And now in this lecture we'll answer two questions. In the first question, we'll find out the area of this big rectangle EHQF, and in the second question, we'll find out the area of this circle using two different methods. So let's start with the first question. In the drawing, we have the big rectangle. This is the big rectangle EHQF. Inside this big rectangle, we have three circles. The radius of this small circle is equal to 5 units in its length. The radius of this medium circle equals to 6 units in its length. And the radius of this big circle equals to 8 units in its length. Again, our test was to find out the area of this big rectangle. So first of all, we know that all the angles inside the rectangle are right angles. So this is a right angle. This is a right angle. This is a right angle. And this is also a right angle. Here we can implement rule 1. According to rule 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. We can implement rule 1. Lots of times in this drawing, we take one example. For example, we have here the radius OB is equals to 6 is drawn to point V. That is the point of tendency of tangent HQ with this medium circle. And whenever you have a radius that is drawn to the point of tendency, then tangent HQ will be perpendicular to the radius BQ. If HQ is perpendicular to BQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So I'll not repeat the same explanation again. Here this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule 1. Likewise, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. We define the point of tendency of tangent FQ with this big circle. This point is point T, and we join point S and T together by straight line. ST is of course the radius of this big circle. It is equals to 8 units in its length. And according to rule 1, this angle equals to 90 degrees. And this angle also equals to 90 degrees. In the small quadrilateral CFTS, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 pieces angle. In total, they must be equal to 360 degrees. According to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4 pieces angle must be equal to 90 degrees in its size. So inside quadrilateral CFST, we have 4 right angles. According to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to quadrilateral CFST as a rectangle, but we also know that the opposite sides of a rectangle are equal to each other. So after CFST, side ST must be equal to the opposite side CF. But ST is 8, therefore the opposite side CF must be also equal to 8 units in its length. We will define the point of tendency of tangent edge Q with this big circle. This point is point L, and we will join points S and N together by a straight line. SL is of course the radius of this big circle. This is equal to 8 units in its length. According to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in quadrilateral STLQ, we have 3 angles, and therefore this fourth missing angle must be equal to 90 degrees in its size. Now we relate to quadrilateral STLQ as left angle, and we also know that the opposite sides of an angle are equal to each other. Anyway, we get that ST equals to LQ, and LQ is also equals to 8 units, but we don't need this information here. What is relevant here, that this is the big angle CSL. The big angle CSL equals to 90 degrees plus 90 degrees, that is 180 degrees. And we know that any angle that is equal to 180 degrees in its side, it is defined as a straight line. Therefore, CL is a straight line. So write it down. Line segment CL is a straight line. Therefore, the big shape ECLH, this is the big shape ECLH, is a quadrilateral. The big shape ECL is a quadrilateral because it has 4 sides. 1, 2, 3, 4. The big shape ESLH is a quadrilateral with 4 right angles. 1, 2, 3, 4. So we can relate to the big quadrilateral ECLH as a rectangle. So write it down. Quadrilateral ECLH is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle ECLF, side CL equals to the opposite side EH. But CL in total equals to 8 plus 8, that is 16. Therefore, the opposite side EH, must be also equal to 16 units in its length. So write it down. This is the opposite side EH. It is equal to 16 units in its length. EH, it is actually the width of the big rectangle EFQH. So we found out that the width of this rectangle EFQH is equal to 16 units. The only thing that is left to find in order to find out the area of this big rectangle EFQH is to find out the length. The length is here. And the width times the length equals to the area of this big rectangle EFQH. We will join points. We'll define the point of tendency of tangent EH with this small circle. This point is point S, and we'll join points P and S together by a straight line. SP is of course the radius of this small circle that is equals to 5 units in its length, and according to rule 1, this angle equals to 90 degrees, and this angle equals to 90 degrees. So in this quadrangle AESP we have 1, 2, 3 right angles, and therefore this fourth missing angle must be equal to 90 degrees in its size. Quadrangle EASP has 4 right angles, therefore we relate to quadrangle EASP as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle EAPS, side SP must be equal to the opposite side EA. But SP is 5, therefore the opposite side EA must be also equal to 5 units in its length. In the next step, we will extend the radius BQ of this medium circle by a straight line until it touches side EF of the big rectangle. Again, we will extend the radius BQ by a straight line until it touches side EF of the big rectangle. And we define the touching point of the extended radius BQ with side EF. This point is point Z. By doing this construction, we created this quadrangle EZBH. Inside this quadrangle EZBH, we have 1, 2, 3 rectangles. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So in this quadrangle ZCLH we have 1, 2, 3 rectangles. Therefore this fourth missing angle must be equal to 90 degrees in its size. So in quadrangle ZCLB we have 4 rectangles, and therefore we can relate to quadrangle ZCLB as a rectangle. So quadrangle ZCLB is a rectangle, but we know that the opposite sides of a rectangle are equal to each other. So the non-quadrangle ZCLB is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ZCLB, side CL must be equal to the opposite side ZB. But CL is 16. Therefore the opposite side ZB must be also equal to 16 units in its length. So ZB equals to 16 units in its length. In the next step, we will do another construction. That is to say, from point P, that is the center of this small circle, we will do perpendicular on ZB. Again, from point P, we will do perpendicular on ZB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and ZB. This point is point D. While doing this construction, we added the small quadrilateral AZDP. Inside the small quadrilateral AZDP, we have 1, 2 vertices, and therefore this fourth integral must be also equal to 90 degrees inside, and therefore quadrilateral AZDP is a rectangle. Again, quadrilateral AZPD is a rectangle, so it is known. But we also know that the opposite sides of the rectangle are equal to each other. So in the small rectangle AZDP, side AB must be equal to the opposite side ZD. But AP is 5, therefore the opposite side ZD must be also equal to 5 units in its length. What is the length of this missing line segment DQ? From the drawing, it is very easy to say that DQ in total equals to ZB minus ZD minus QB. Repeat again, DQ in total equals to ZB minus ZD minus QB. So DQ equals to ZB is 16 minus ZD is 5, 16 minus 5 is 11, minus QB, that is 6, and 11 minus 6 is 5. So in total, if you found out that DQ equals to 5 units in its length. This is the missing line number DQ is equal to 5 units in its length. In the next step, we'll join points P and Q together by straight line. Point P is the center of this small circle, point Q is the center of this medium circle. So PQ is the distance between the centers of those two circles. So we joined the center of those two circles by a straight line. PQ is the distance between the center of those two circles. The small circle touches the medium circle at this point. We define the touching point, this point X. So the small circle has an external edge between these mediums. With this medium circle is point X. Whenever you have an external edge between two circles, you can implement rule 10. So repeat quickly rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes for their touching points. In the drawing we have two circles that touch each other externally at point K. The center of this circle is at point O. The center of this circle is at point M, and the straight line that connects the centers together is of course the straight line OM. And according to this rule 10, the straight line OM must pass through point K, that is their touching point. Again, the straight line OM must pass through their touching point, that is point K, or OKM is one straight line. Again, OKM is one straight line. So we can implement rule 10 in our drawing, because we have an external between those two circles at point X. The center of this small circle is at point P, the center of this circle is at point Q. The straight line that connects the centers together is of course the straight line PQ. And according to rule 10, the straight line PQ must pass through their touching point, that is point X. Again, the straight line PQ must pass through point K, that is their touching point. Or PXQ is one straight line. PXQ is one straight line. PXQ is one straight line according to rule 10. PX is the radius of this small circle that is equals to 5. QX is the radius of this medium circle. Is the radius of this medium circle that is equals to 6. According to what is given in the question. And because of the fact that PXQ is one straight line, it means that PQ must be equal to PX plus XQ. So PQ equals to PX, that is 5, plus XQ, that is 6. So in total, PQ equals to 5 plus 6, that is 11. PQ equals to 11 units in its length, according to rule 10. In the next step, I'm copying this right green triangle PDQ in a new page, and we will implement in this right green triangle PDQ the Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the variation for Pythagoras theorem. So actually, this is the right green triangle PDQ, that according to the original drawing. This right green triangle, this right triangle PDQ, according to the Pythagoras theorem, PQ squared, that is the square of the hypotenuse, equals to PD squared plus DQ squared. So I write it down. PQ squared, that is the square of the hypotenuse, equals to PD squared plus DQ squared. PQ is 11, therefore PQ squared is 11 squared, that is 121, and it is equals to PD squared. PD is the missing sign, so we use it is. So it is PD squared plus DQ squared. DQ is 5, therefore DQ squared is 5 squared, that is 25. So in total, we should find out that 121 equals to PD squared plus 25. Here we subtract 25 from this equation, and we get that 121 minus 25 is 96 equals to PD squared. 96 is 16 times 6, so we'll substitute 96 by 16 times 6. 16 times 6 equals to PD squared. Here we'll take a root out of this equation, and finally we get that PD, the missing sign PD, is equal to the square root of 16 is 4, so inside the root we left only with 6. So in total we found out that the length of line segment PD is equal to 4 times root of 6 units. So this is actually line segment PD is equal to 4 times root of 6 units in its length. Quadrangle AZDQ AZDP is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. So in rectangle AZDP, side PD must be equal to the opposite side AZ. But PD is 4 times root of 6, therefore the opposite side AZ must be also equal to 4 times root of 6 units in its length. In the next step, we'll join the center of this medium circle, this point Q, with the center of this big circle, this point S point S. So we join points Q and S together by straight line. Actually, QS is the distance between the center of the medium circle and the big circle. In the next step, we will do a construction. That is to say, from point Q, that is the center of this medium circle, we will do perpendicular on CL. From point Q, we will do perpendicular on CL. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point Q and CL. This point is point Y. So, by doing this construction, we can edit here quadrangle QYLB. This is quadrangle QYLB. In quadrangle QYLB, we have 1, 2, 3 rectangles, and therefore this fourth missing angle must be also equal to 90 degrees in its size. Quadrangle QYLB is 4 rectangles, and therefore quadrangle QYLB is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in this quadrangle QYLB, side QB must be equal to the opposite side YL, but QB is 6, therefore the opposite side YL must be also equal to 6 units in its length. We know that QL is the radius of this big circle, that is equals to 8. We just now found out that YL equals to 6. And therefore the short line segment SY is equal to SL minus YL. Again, SL minus YL equals to SY. So write it down. If you found out that SY, the short line segment SY is equal to SL, that is the radius of the big circle, that is equal to 8, minus YL, that is 6. So SY equals to 8 minus 6, that is 2. This is the short line segment SY, that is equals to 2 units in its length. Because of the fact that this medium circle touches this big circle at this point, first of all we define your touching point. This point is point J, according to rule 10. So we have here an acceleration between the medium circle and the big circle at point J, according to rule 10. The third line that connects the circles together, that is QS, must pass through point J, that is their touching point. Or QJS is one side line. Again, QJS is one side line according to rule 10. QJ is the radius of this medium circle, that equals to 6 units in its length. SJ is the radius of this big circle, that is equal to 8 units in its length. And because of the fact that according to rule 10, SJQ is one side line, it means that SQ equals to SJ plus JQ. So SQ in total equals to SJ, that is 8, plus JQ, that is 6. So in total SQ equals to 8 plus 6, that is 14. So in the next step, I'll copy this green right triangle QSY in a new page, and we will implement the Pythagoras theorem on this green right triangle QSY. The hypotenuse SQ equals to 14, side SY equals to 2, and QY is the only missing side. We find out the length of side QY by implementing the Pythagoras theorem on this green right triangle QSY. Here by PT is the derivation for Pythagoras theorem. So actually, this is the right triangle QSY, the right green triangle QSY that they copied from the original drawing. According to the Pythagoras theorem, in this right triangle QSY, SQ squared, that is the square of the hypotenuse, equals to SY squared plus YQ squared. So I write it down. SQ squared, that is the square of the hypotenuse, equals to SY squared plus YQ squared. SQ is 14, therefore SQ squared is 14 squared, that is 196, and it is equals to sy squared. Sy is 2, therefore sy squared is 2 squared, that is 4, plus yq squared. Yq is the missing side, so we leave this it is, so it is plus yq squared. So 196 equals to 4 plus yq squared. Here we'll subtract 4 from this equation, and we get that 196 plus 4 is 192 equals to yq squared. Here we'll substitute 192 by 64 times 3 equals to yq squared. Here we'll take a root out of this equation, and we get that the missing side yq is equal to the square root of 64, that is 8. So inside the root we'll have to leave 3. So in total we found out that the missing side yq equals to 8 times square root of 3 units in its length. So write down. This is the missing side yq is equals to 8 times square root of 3 units in its length. In quadrangle ZC YQ, in this quadrangle ZCYQ, we have 1, 2, 3 integers. Therefore, this fourth missing integral must be also equal to 90 degrees in its size. And therefore, this quadrangle ZCYQ is a rectangle because it has 4 right angles. But we also know that the opposite sides of an rectangle are equal to each other. So in rectangle ZCYQ, side YQ must be equal to the opposite side CZ. But YQ is 8 times square root of 3, therefore the opposite side CZ must be also equal to 8 times square root of 3 units in its length. So we actually found out that the length of EF, side EF of the rectangle, is equal to 5 plus 4 times square root of 6, but plus 8 times square root of 3 plus 8. This is the length. The width is EH, that is 16, and the length times the width is the area of this big rectangle EF QH. EF QH. And that will be the answer to the question. So the area of rectangle EFQH is equal to the width for the rectangle times the length. The width of rectangle EFQH is the edge, and the length is EF. Again, the length is EF. The width EH equals to 16 units. And the width EF in total equals to EA plus AZ plus ZC plus CF. So the area of a triangle EFQH is equal to the width, that is 16, times the length, is equals to EA is 5, plus AZ is 4 times root of 6, plus ZC, that is 8 times root of 3, plus CF, that is 8. So total the area of a triangle EFQH is equals to 16 times 5 plus 4 times root of 6 plus 8 times root of 3 plus 8. Actually, the value of this expression is equal to 586.47 square units. So actually, we found out that the area of this big rectangle EFQH is equal to 586.47 square units. And that is the answer to the first question. In the next step, I will present to you the second question, and we will solve the second question by using two different methods. In the second question, our task is to find out the area of this circle. So in the moment we have a circle, this is called AB, that is equal to 8 units in itself. This is called DQ, that is equal to 6 units in itself. This is angle PMQ, that is a right angle. Again, our task is to find out the area of this circle. So we'll start with the first method. So I will present to you rule 29, and we will implement rule 29 in our drawing. According to rule 29, peripheral angles that subtend on the same arc are equal to each other in their sizes. So this is a circle. In the moment we have a circle. This is peripheral angle BDC. This equals to alpha degrees in its size, and the peripheral angle BDC subtend on arc BC. Again, peripheral angle BDC subtend on this arc BC. Likewise, we have another peripheral angle, that is angle BEC. This equals to beta degrees in its size, and peripheral angle BEC also subtend on the same arc BC. And because of the fact that those two peripheral angles are both subtend on the same arc BC, they must be equal to each other in their sizes. That is to say, alpha equals to beta. So according to this rule 29, if two peripheral angles subtend on the same arc, they must be equal to each other in their sizes. In this case, those two peripheral angles subtend on the same arc BC, therefore they are equal to each other in their sizes. That is to say, alpha equals to beta. We can implement rule 29 in our drawing. Why? Because if we focus on this arc BQ, this is arc BQ. The red curve is arc BQ. This is arc BQ. And this is peripheral angle BAQ that subtend on arc BQ. Likewise, this is peripheral angle QPB that is also subtend on the same arc BQ. And because of the fact that those two peripheral angles subtend on the same arc BQ, they must be equal to each other in their sizes. So if we define the size of this angle S alpha. Then the size of this perpendicular must be also equal to alpha, because they are both subtend on the same arc BQ. And they are equal to each other according to rule 29. In the next step, we will focus on this arc AP. So this is arc AP, and peripheral angle ABP subtend on arc AP. Again, this is peripheral angle ABP that subtend on arc AP. And we also have another peripheral angle. This is peripheral angle AQP that subtend on the same arc AP. And because of the fact that those two peripheral angles subtend on the same arc AP, they must be equal to each other in their sizes according to rule 29. So if we define the size of this peripheral angle ABP is beta, then the size of this peripheral angle AQP must be also equal to beta, because they both subtend on the same arc AP. Therefore they are equal to each other according to rule 29. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. This vertex angle equals to 90 degrees according to what is given as the equation. Therefore, the opposite vertex angle must be also equal to 90 degrees in its size. So this is the right triangle A and B. The sum of the angles in this right triangle A and B must be equal to 180 degrees according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have in the right triangle, triangle A and B? Alpha plus beta plus 90 degrees. In total, they must be equal to 180 degrees according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Here we'll subtract 90 degrees from this equation, and we'll get that alpha plus beta equals to 190 degrees minus 90 degrees is 90 degrees. So alpha plus beta equals to 90 degrees. Here we will multiply this equation by 2, and we get that 2 alpha plus 2 beta equals to 180 degrees. And again, we have found out that 2 alpha plus 2 beta equals to 180 degrees. In the next step, I will present to you rule 13, and we will implement rule 13 in our drawing. But before that, we define the center of this circle. This point is point O. So according to rule 13, the center angle is twice as large as the peripheral angle subtended on the same chord or the same arc. Doesn't matter if it is a chord or arc. So in the drawing we have a circle. This is peripheral angle ACB that subtend on arc AB or chord AB, doesn't matter. Likewise, this is center angle AOB that subtend on the same arc AB. Because of the fact that the center angle subtend on the same arc as this peripheral angle ACB, therefore the size of the center angle must be twice as big as the size of this center angle that subtend on the same arc RKB. The size of this peripheral angle ACB is theta, and therefore the size of this center angle must be equal to theta. So according to this rule 13, the size of a peripheral angle is twice as large as the size of the size of a center angle is twice as large as the size of the peripheral angle that subtend on the same arc or the same chord. Okay. Repeat again. The size of the center angle is twice as large as the size of a peripheral angle that subtend on the same arc. Can implement rule 13 in our drawing. We will create peripheral angle that subtend on RKP. So we created peripheral angle AOP that subtend on RKP. Here we have again, this is center angle AOP that subtend on RKP. But we have also peripheral angle AQP that subtend on the same arc RKP. And the size of peripheral angle AQP is beta. And therefore, the size of the center angle AOP that subtend on the same arc RKP must be equal to 2 beta. This twice as large of this peripheral angle that subtend on the same arc RKP. So the size of the center angle AOP is 2 beta, according to rule 13, of course. In the next step, we create another center angle that subtend on arc BQ. Again, we create another center angle that subtend on this arc RQB. So okay, this is center angle QOB that subtend on RQB. But we also have peripheral angle QAB that is also subtend on the same arc RQB. Center peripheral angle QAB equals to alpha, therefore center angle QOB that subtend on the same arc RQB must be equal to 2 alpha. This twice as large as this peripheral angle that subtend on the same arc RQB. So according to rule 13, center angle BOQ equals to 2 alpha. In the next step, we define angle POQ. This angle is X, and we define this angle AOB. This angle is Y. We have the rule that states that the sum of the angles around any point is equal to 360 degrees. On the rule, the sum of the angles around any point is equal to 360 degrees. And therefore, the sum of the angles around point O, that is the center of the circle, must be equal to 360 degrees. So, write it down. If we focus on point O, that is the center of the circle, the sum of the angles around point O must be equal to 360 degrees, according to the rule that I mentioned. So which angles we have around point O? We have this angle that is 2 alpha. plus this angle that is 2 beta plus this angle x plus this angle y. In total, the sum of those four angles must be equal to 360 degrees. And again, if you focus on point O that is at the center of the circle, the sum of those four angles must be equal to 360 degrees. That is to say, 2 alpha plus 2 beta plus x plus y equals to 360 degrees. But we already found out that 2 alpha plus 2 beta equals to 180 degrees. Here, 2 alpha plus 2 beta equals to 180 degrees. Therefore, we can substitute 2 alpha plus 2 beta in this equation by 180 degrees. We'll do it now. We get that 2 alpha plus 2 beta is 180 degrees. Plus x plus y equals to 360 degrees. Here we subtract 180 degrees from this equation, and we'll get that x plus y equals to 360 degrees minus 180 degrees is 180 degrees. So, total we shall find out that x plus y equals to 180 degrees. Okay, again, x plus y equals to 180 degrees. In the next step, I'll present to you Rule 30, and we'll implement Rule 30 in our drawing. So according to Rule 30, center angles that subset on equal chords are equal to each other. In the drawing we have a circle. This is center angle COD. This equals to alpha degrees in its size, and it's subset on chord CD. Likewise, we have another center angle. This is angle BOA. This center angle that is equals to beta degrees in its size, and it's subset on chord AB. According to this rule, Rule 30, if chord AB equals to chord CD, then those two periferials must be equal to each other in their sizes. That is to say, alpha equals to beta. Again, if chord AB equals to chord CD, then alpha equals to beta. So according to this rule, Rule 30, center angles that subset on equal arcs, like here, if AB equals to CD, then they must be equal to each other in their sizes. Then they are equal to each other in their sizes. In this case, if chord AB equals to chord CD, then those two periferials are equal to each other in their sizes. That is to say, alpha equals to beta. So we can implement Rule 30 in our drawing. So first of all, I'll copy this circle in a new page, and I'll copy this center angle A or B that equals to y degrees in its size with its chord AB. that is equals to 8 units in its size. And then I will copy triangle POQ. I will copy it in such a way that it will be adjacent to triangle AOB. So first of all, I'll copy this circle in a new page. So actually, those two circles are identical. And then point O is the center of the circle. In the next step, I'll copy this center AOB with code AB. So actually, I copied triangle AOB from the original domain. Triangle AOB equals to y degrees in its size, and its subset on code AB. In the next step, from point B, I will draw code that is equals to 6 degrees in its units according to my construction. So this is called BC. And again, this is called BC. Code BC equals to 6 units in its length according to my construction. And we will join point C and all together by a straight line. So by doing this construction, we created triangle BOC. This is triangle BOC. That subset on code BC that equals to 6 units in its length. In the original domain, we have triangle POQ that equals to 6 degrees in its size, that is equals to x degrees in its size, and its subset on code PQ that is equals to 6 units in its length. And because of the fact that those two peripherals, they are both subset on equal chords, they both subset on chord that is equals to 6 units in itself, they must be equal to each other in their sizes according to rule 30. According to rule 30, straight triangles that subset on equal chords are equal to each other in their sizes. Those two straight triangles, the subset on equal chords. The length of the chord is 6. Therefore, they must be equal to each other in their sizes. but the size of this center triangle POQ is x. Therefore, the size of this center triangle COB must also equal to x, because they both subtend on equal chords. They subtend on chord that is equal to 6 units in its length. Therefore, they must be equal to each other in their sizes. So if the size of this peripheral angle is x, then the size of this peripheral angle, if the size of this center triangle is x, then the size of this center triangle must be also equal to x, because they are equal to each other according to rule 30. By doing this construction, we can obtain the big angle AOC. This is the big angle AOC. That is equal to x plus y. Again, the big angle AOC equals to x plus y degrees in its size. But we already found out that x plus y equals to 180 degrees. So the big angle AOC is equal to x plus y. It is actually equals to 180 degrees in its size. And we know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. Therefore, AC is a straight line. But AC is a straight line that touches the circle 2 points, A and C. Therefore, AC is a chord. AC is a chord. AC is a chord that passes from point O, that is the center of the circle. AC is a chord that passes from point O that is the center of the circle. And we know that any chord that passes through the center of the circle is defined as a diameter. But again, any chord that passes through the center of the circle, it is defined as a diameter. Therefore, AC, chord AC that passes from point O, that is the center of the circle, it is the diameter of the circle. So AC is the diameter of the circle. The diameter is twice as long as the radius. So the radius of this circle is R, AC must be equal to 2R. So AC is the diameter of the circle. Here we can implement rule 7 in our drawing. Repeat quickly on rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. In the drawing, we have a circle. This is peripheral angle ACB that subtends on chord AB, that is the diameter of the circle, and therefore, according to this rule 7, peripheral angle ACB must be equal to 90 degrees in its size. We can definitely implement rule 7 in our drawing, because in our drawing we have peripheral angle ABC that subtends on chord AC, that is the diameter of the circle, and therefore, according to rule 7, peripheral angle ABC must be equal to 90 degrees in its size, because it subtends on the diameter of the circle. So peripheral angle ABC equals to 90 degrees in its size. It is a right angle according to rule 7. So in the next step, I'll copy the right triangle ABC in a new page, and we'll implement the quadratic theorem on this right big triangle ABC. The diameter AC is 2R, twice as long as the radius. AB is 8 and BC is 6. So copy this right triangle ABC in a new page, and we implement on it the Padala theorem. But again, the diameter AC equals to 2R. Side AB equals to 8 units in its length. And side BC equals to 6 units in its length according to our construction. Here by PT is the proportion for Pythagoras theorem. So actually, this is the right triangle ABC, this is according to the original drawing. In this right triangle ABC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. AC is 2R, therefore AC squared is 2R squared, that is 4R squared, and that is equals to AB squared. AB is 8, therefore AB squared is 8 squared, that is 64, plus BC squared. BC is 6, therefore BC squared is 6 squared, that is 36. 64 plus 36, 64 plus 36 is 100. So in total we should find out that 4R squared equals to 100, or 4R squared equals to 100. Here we will divide this equation by 4. And you get that R squared equals to 100 over 4 is 25. So R squared equals to 25. Here we take a root out of this equation and you get that the radius R of the circle is equals to the square root of 25, that is 5. We should find out that the radius of this circle R equals to 5 units. Our task is to find out the area of the circle. Actually, you know that the area of any circle equals to pi times the radius of the circle squared. And again, the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is r squared. So the area of our circle must be equal to pi r squared. So it is pi times r squared. R is 5, therefore r squared is 25. So in total we found out that the area that we are looking for in this question, that is the area of this circle, equals to either 25 pi square units in its size, or in terms of numbers it is equal to 78.54 square units in its size. But again, we found out that the area of this circle is equal to either 25 pi square units in its size, or in terms of numbers, the area of this circle equals to 78.54 square units in its size. So we finished with the first method. In the next step, I will present to you how to find out the area of this circle according to the second method. In the second method, we use some of the things that we already found out in the first method. In the first method, we have already found out that In the first method, we already found out that those two angles are both equal to alpha. Point O is the center of the circle. Those peripheral angles are both equal to 90 degrees, according to the rule that vertex angles, those two vertex angles are equal to each other, according to the rule that vertex angles are equal to each other. So this angle equals to 90 degrees. So this is the right angle A and B. In this right angle A and B, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in a triangle. Likewise, in this right angle PMQ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha, according to the sum rule that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see from the drawing that those two right angles are similar to each other, according to angle, similarity rule. I will explain anyway why those two right angles are similar to each other. First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if you found out that all the three angles of this right angle ABM are correspondingly equal to all those three angles of this right angle PMQ, and therefore those two right angles are similar to each other according to angle similarity rule. So I write it down. We actually found out that the right big triangle A and B is similar. This is the sign of similar to the right triangle PMQ, this right triangle, according to angle similarity rule. And from the fact that those two right angles are similar to each other, we will derive that the following relationship exists between their sides. We derive that side AB of the right triangle A and B over side PQ of the right triangle PMQ is equal to side AM of the right triangle A and B over side PM of the right triangle PMQ, and it is also equals to side AB of the right triangle A and B over side QM of the right triangle PMQ. Repeat again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AB of the right triangle A and B over side PQ of the right triangle PMQ is equals to side AM of the right triangle A and B over side PM of the right triangle PMQ, and this is also equals to side MB of the right triangle A and B over side MQ of the right triangle PMQ. AB is 8. Over PQ is 6, and it is equals to AM over PM. Here again, we found out that 8 over 6 equals to AM over PM. Here we will divide both the numerator and the denominator of this number by 2, and we get that 8 over 2 is 4 and 6 over 2 is 3. So 3/3 equals to AM over PM. Here we multiply both the numerator and the denominator of this number by A, and we get that A over A is A over A is 1, therefore it is allowable to multiply this number by A over A. So 4A over 3A equals to AM over PM. What is the meaning of this equation? The meaning of this equation is that if AM equals to 4A, then PM must be equal to 3A. This is the meaning of this equation. Repeat again. The meaning of this equation is that if AM equals to 4A, then PM must be equal to 3A. So if you found out that if AM equals to 3A, if AM equals to 4A, AM equals to 4A, so if AM equals to 4A, if AM equals to 4A, then PM must be equal to 3A. Those two sides of the equation also equal to each other. AB over PQ is 4/3, so 4/3 equals to MB over QM. Four thirds equals to MB over QM. Here we will multiply both the numerator and the denominator of this of the equation by B. Again, B over B is 1, therefore it is allowable to multiply anything by 1. We will not change the value of the expression by multiplied by 1. So the operation is allowable. So 4B over 3B equals to MB over QM. What is the meaning of this equation? The meaning of this equation is that if MB equals to 4B, then QM must be equal to 3B. Again, according to this equation means that if MB equals to 4B, then QM must be equal to 3B. So at the time we found out that if MB equals to 4B, then QM must be equal to 3B. PB is a chord inside this circle, so PB is a chord, it is absolutely a straight line. So if you focus on the right side of the straight line PB at point M, the sum of the angles here must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the right side of PB is point M? We have this angle that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we will join points B and Q together by straight line. By joining points B and Q, we create the right angle MBQ. This is the right angle MBQ. So I'll copy this right angle MBQ in a new page, and we will implement the Pythagoras theorem on this right angle triangle MBQ. Side MB equals to 4B units in its length, and side MQ equals to 3B units in its length. BQ is the missing side. Here by PT is the abbreviation for Pythagoras theorem. So actually, this is right angle BMQ that is according to the original drawing. This right angle BMQ according to the Pythagoras theorem, BQ squared, that is the square of the hypotenuse, equals to MB squared plus MQ squared. So I write it down. BQ squared, that is the square of the hypotenuse, equals to MB squared plus MQ squared. BQ is the missing side, so we leave it as it is, so it is BQ squared equals to MB squared. MB is 4B, therefore MB squared is 4B squared. It is 16B squared plus MQ squared. MQ is 3B, therefore MQ squared is 3B squared. This is 9B squared. 16B squared plus 9B squared is 25B squared. So in total, we should find out that BQ squared equals to 25B squared. Here we take a root out of this equation and finally get that BQ, the missing side BQ, is equal to the square root of 25, that is 5, times square root of B squared, that is B. So in total, we should find out that the missing side BQ equals to 5B units in its length. This is the missing side BQ. This equals to 5B units in its length. In the next step, we focus on this right triangle, on this big triangle ABQ. And we will calculate the area of this triangle ABQ in two different methods. Repeat again. we calculate the area of this triangle ABQ in two different methods, and then we get an equation that says the area of triangle ABQ according to the first method must be equal to the area of triangle ABQ according to the second method. Okay, so first of all, we calculate the area of this triangle ABQ according to the first method. We know that the area of any triangle equals to the base of the triangle times the height to the base over 2. So the area of this triangle ABQ must be equal to, we'll choose the base SAQ, the base AQ times the height to the base, that is BM. Why the height is BM? Because it's greater than 90 degrees with the base AQ. Not triangles, they are both right angles. So it is the height times the height BM over 2. So according to the first method of calculation of the area of triangle ABQ, the area of triangle ABQ is equal to the base AQ times the height to the base, that is BM over 2. In the next step, we calculate the area of triangle ABQ in the first method. In the second method, this is triangle ABC. That could be any triangle. Side AB of triangle ABC equals to A units in itself. Side AC equals to B units in itself. Side BC equals to C units in itself. This is angle theta. In this triangle ABC, the area of this triangle ABC is equals to A times B times sinus theta over 2. Again, the area of triangle ABC, this triangle ABC that could be any triangle, is equal to the multiplication of two sides by each other, that is A times B, times sinus of the angle between the two sides, that is sinus theta over 2. And again, the area of this triangle ABC that could be any triangle is equal to A times B times sinus theta over 2. We use the new formula in order to calculate the area of this triangle, triangle ABQ. According to the new formula, the area of triangle ABQ will be equal to, this is triangle ABQ, the area will be equal to the multiplication of two sides by each other. So that is, when you choose the side AB, will be multiplied by side BQ. So it is AB times BQ times sinus the angle between those two sides. The angle between those two sides is this angle, angle ABQ. So it is times sinus angle ABQ. Again, it is times sinus the angle between those two sides, AB and BQ, that is angle ABQ. This is angle ABQ. So it is times sinus angle ABQ divided by 2. Because again, according to the second method, we actually found out that the area of triangle ABQ equals to AB times BQ, that is the multiplication of two sides by each other, times sinus the angle between those two sides, AB and BQ, that is sinus angle ABQ over 2. So we created a question that says that the area of triangle ABQ according to the first method must be equal to the area of triangle ABQ according to the second method. Here we have 2 on both sides of the equation, so 2 will get cancelled. In the next step, we'll find out the value of sinus angle ABQ. In order to find out the value of sinus angle ABQ, we use the law of sines. The law of sines is true in any triangle. This is a triangle ABC that could be any triangle. The length of side ABC, side AC equals to B units in its length, side BC equals to A units in its length. This is angle alpha, this is angle beta, and this is angle gamma. This triangle ABC that could be any triangle, the following equation is true. that A over sinus alpha over B over, again, A over sinus alpha equals to B over sinus beta equals to C over sinus gamma equals to 2R. And 2R is the diameter of the circle that blocks this triangle. Again, 2R is the diameter of this circle that blocks this triangle. According to the law of sines, the following equation is true. In this triangle ABC, that could be any triangle. A over sinus alpha equals to B over sinus beta equals to C over sinus gamma equals to 2R. And 2R is the diameter of the circle that blocks this triangle ABC. We can definitely implement the law of sines in our drawing. But you should notice that we take the side and the angle in front of the side. It is A over sinus the angle between over sinus the angle that is in front of A. Here we also have C over sinus the angle in front of C, and we have B over sinus beta. B over sinus the angle that is in front of B, that is beta, sinus beta. So we can definitely implement the law of sines in our drawing, because the law of sines is true in any triangle. Therefore we can implement the law of sines in this triangle, triangle ABQ. This triangle ABQ is blocked by this circle, and therefore 2R will be the diameter of this circle that blocks this triangle, triangle ABQ. So we have to take AQ over sinus angle ABQ. Again, it will be AQ over sinus angle that is in front of AQ, that is angle ABQ. So AQ over sinus angle ABQ equals to 2R, and 2R is the diameter of this circle that blocks this triangle ABQ. So according to the law of sines, the following equation is true. AQ over sinus angle ABQ equals to 2R. Again, this equation is the implementation of the law of sines in our drawing. We took side AQ over sinus angle that is in front of AQ, that is angle ABQ. So it is AQ over sinus angle ABQ that is equal to 2R. And 2R is the diameter of this circle that blocks triangle ABQ. So AQ over sinus angle ABQ equals to 2R. Here we multiply this equation by sinus angle ABQ, and we divide it by 2R simultaneously in order to find out the value of sinus angle ABQ. And we get that sinus angle ABQ equals to AQ over 2R. Again, we multiply this equation by sinus angle ABQ, and we divide it by 2R simultaneously. In this way we found out that sinus angle ABQ equals to AQ over 2R. And because of the fact that sinus angle ABQ equals to AQ over 2R, it means that we can substitute sinus angle ABQ in this equation by AQ over 2R. We'll do it now, and we get that AQ times BM equals to AB times BQ times sinus angle ABQ. And sinus angle ABQ equals to AQ over 2R. So in total we found out that AQ times BM equals to AB times BQ times AQ over 2R. Here we have AQ on both sides of this equation, so AQ will get cancelled. After we cancel AQ, this side of the equation we left only with BM. That is equal to AB times BQ over 2R. Here we multiply this equation by R and we divide it by BM simultaneously. And we get that R equals to AB times BQ over 2BM. So if you found out that the radius of this circle R equals to AB times BQ over 2 times BM. So R equals to AB. AB is 8. Times BQ. BQ is 5B. Over 2 times BM. BM is 4B. We have 8 in the numerator, and 2 times 4 is 8. So those two expressions will get cancelled. B will be in the numerator and B in the denominator, so B also gets cancelled, and we left only with 5. So if you found out that the radius of the circle R equals to 5 units in its length, our task is to find out the area of this circle. So actually we know that the area of any circle equals to pi times the radius of the circle squared. I repeat again, the area of any circle equals to pi times the radius of the circle squared. And therefore the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle is R, therefore the radius squared is R, so it is pi R squared, but R is 5. Therefore R squared is 5 squared, that is 25. So pi R squared is 25 pi. In terms of numbers, 25 pi is 78.54 square units in its size. So in both methods, we found out that the area of this circle, that is the area that we are looking for in this question, is equal to either 25 pi square units in its size, or in terms of numbers, the area of this circle equals to 78.54 square units in its size. So we finish with the second method, in the second question. In the next step of some other lecture, we'll start with the first question, of course. In the first question, our task was to find out in the first question, our task was to find out the area of this big rectangle EFQH. So in the domain we have the big rectangle EFQH. Inside this big rectangle we have three circles that are tangent to each other. The radius of this small circle equals to 5 units. The radius of this medium circle is 6 units. The radius of this big circle is equal to 8 units in its length. Again, our task is to find out the area of this big rectangle EFQH that blocks those three circles. So, first of all, we know that all the angles inside the rectangle are right angles. So those four angles are all right angles. And we implemented rule 1 in our domain a lot of times. According to rule 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. Repeat again, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So I will explain only one time, and then we will immediately implement the rule without any explanation. For example, we take this medium circle, the radius of this medium circle QB equals to 6. The radius QB is drawn to point B, that is the point of tendency of tangent AQ with this medium circle. And whenever you have radius that is drawn to the point of tendency, then tangent HQ will be perpendicular to the radius BQ. If HQ is perpendicular to BQ, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. Now we implement rule 1 a lot of times. This drawing, we have there's SL. So this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. Likewise, this angle equals to 90 degrees and this angle also equals to 90 degrees according to the same rule, rule 1. We joined point S and T together by a straight line. So this angle equals to 90 degrees, this angle also equals to 90 degrees according to rule 1. Must mention that if Q is tangent to this big circle at point T. So this angle equals to 90 degrees and this angle also equals to 90 degrees according to the same rule 1. Here also, according to rule 1, this angle equals to 90 degrees and this angle also equals to 90 degrees. And we actually joined the points, we extended the radius CS until it touches, we extended the radius CS, we joined points C and L together by a straight line. So SL is the radius of this big circle, that is 8. And here we have quadrilateral STQL. Inside quadrilateral STQL we have 1, 2 furthers, and therefore this fourth circle must be equal to 90 degrees in its size, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Likewise, in this upper small quadrilateral CFTS. We have 1, 2 furthers, and therefore this fourth triangle must be equal to 90 degrees in its size. So actually the big angle CSL, this is the big angle CSL, is equal to 90 degrees plus 90 degrees, that is 180 degrees. And we know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. Therefore, CL is a straight line. And therefore, the big shape ECL edge has 1, 2, 3, 4 sides. Therefore, ECL edge is a quadrilateral. It is a quadrilateral with 4 rectangles. 1, 2, 3, 4. And therefore, it is a rectangle. So in the big rectangle ECL edge, side CL must be equal to the opposite side EH. But CL in total equals to 8 plus 8, that is 16. Therefore, the opposite side EH must be also equal to 16 when it's in its length. So we found out that the width of this big rectangle EHQF is 16. The only thing that is left to find out the length EF, and the width times the length is the area of this big rectangle EFQH. So here in this small quadrilateral we have 1, 2, 3 rectangles, and therefore this fourth rectangle must be equal to 90 degrees in size, and therefore quadrilateral ESAP is a rectangle. Note that the opposite sides of the rectangle are equal to each other. So the small rectangle EFPS side SP must be equal to the opposite side EA. But SP is 5, therefore the opposite side EA must be also equal to 5 units in its length. In the next step we did a construction, that is to say from point P, that is the center of this small circle, we do perpendicular on ZB. Again, from point B we do perpendicular on ZB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and ZB. This point is point D. By doing this construction, we get the quadrilateral AZDP. Inside this quadrilateral AZDP, we have 1, 2, 3 rectangles, and therefore this fourth rectangle must be equal to 90 degrees in its size. Therefore, quadrilateral AZDP is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle APZD, side AP must be equal to the opposite side ZD. But AP is 5, therefore the opposite side ZD must be also equal to 5 units in its length. So ZD is 5, QB is 6, it is the radius of this medium circle. So DQ is the missing side. DQ must be equal to ZB minus ZD minus QB. Again, DQ must be equal to ZB minus ZD minus QB. So DQ equals to ZB, that is 16, minus ZD, that is 5. 16 minus 5 is 11, minus QB, that is 6. 11 minus 6 is 5. So the missing side DQ must be equal to 5 units in its length. In the next step, we join the center of this small circle, point P, with the center of this medium circle, that is Q. Join point P and Q together by straight line. Those two circles have an external arc between them at point Q. Whenever we have external arc between two circles, we can implement rule 10. According to rule 10, the straight line that connects the center of two circles with an external arc between them must pass through their tangent points. So the straight line PQ must pass from point X, that is the touching point, or PXQ is one straight line. PXQ is one straight line. PX is the radius of this small circle, that is 5. QX is the radius of this medium circle, that is 6. And because of the fact that PXQ is one straight line, it means that PQ equals to PX plus XQ. So PQ equals to PX, that is 5, plus XQ, that is 6. So PQ in total equals to 5 plus 6, that is 11. In the next step, I copied the real right triangle PDQ in a new page and implemented the Pythagorean theorem of this right green triangle PDQ. So actually, this is the right triangle PDQ, that is the common of the original domain. In this right triangle PDQ, PQ squared, that is the square of the hypotenuse, must be equal to PD squared plus DQ squared. PQ squared equals to PD squared plus DQ squared. PD is 11, therefore PD squared is 11 squared, that is 129, and it is equals to PD squared. PD is the missing side of which is, so it is PD squared plus DQ squared. DQ is 5, therefore DQ squared is 5 squared, that is 25. So total we found out that 121 equals to PD squared plus 25. Here we subtract 25 from this equation, we found out that 121 minus 25 is 96. So 96 equals to PD squared. We substituted 96 by 16 times 6, so 16 times 6 equals to PD squared. Here we took out of this equation, and we found out that PD equals to the square root of 16, that is 4. So inside the root we left only with 6. So PD in total equals to 4 times square root of 6 units in its length. So here, this is nice PD, that equals to 4 times square root of 6 units in its length. We already found out that quadrangle AZDP is a rectangle. So in this rectangle, the opposite sides are equal to each other. That is to say, side PD must be equal to the opposite side AZ. But PD is 4 times square root of 6, therefore the opposite side AZ must be also equal to 4 times square root of 6 units in its length. In the next step, we join points Q with point S. Point Q is the center of the medium circle, point S is the center of this big circle. Those two circles have an external line between them, and this point J. Therefore, we can implement a rule 10. According to rule 10, the straight line QS that connects the centers together must pass through point J, that is their touching point. Or QJS is one straight line. QJS is one straight line according to rule 10. If QJS is one straight line, it means that QS in total must be equal to QJ, that is 6, plus JS, that is 8. So total QS must be equal to 6 plus 8, that is 14. So QS equals to 14 units in its length according to rule 10. In the next step, we did another construction, that is to say, from point Q we drew perpendicular on CL. Again, from point Q we drew perpendicular on CL. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and CL. This point is point Y. By doing this construction, we created quadrangle QYLB. Inside quadrangle QYLB, we have 1, 2, 3 rectangles, and therefore this fourth rectangle must be equal to 90 degrees in its size. Therefore, quadrangle QYLB is a rectangle. But we also know that the opposite sides of rectangle are equal to each other. So in rectangle QYLB, side QB must be equal to the opposite side YL. But QB is 6, therefore the opposite side YL must be also equal to 6 units in its length. So what is the length of this short line segment SY? SY must be equal to SL minus YL. Again, SL minus YL equals to SY. And again, here we have SY equals to SL minus YL. So SY equals to SL. SL is the radius of this big circle, that is 8, minus YL. YL is 6. So SY in total equals to 8 minus 6, that is 2. This short line segment SY equals to 2 units in its length. So in the next step, I copy this right green triangle QSY in a new page and implemented the pattern on this green right triangle QSL. This is the right triangle QSL, that is according to the original domain. In this right triangle QSL, QS squared, that is the square of the hypotenuse, equals to SY squared plus YQ squared. The hypotenuse QS is 14, therefore QS squared is 14 squared, that is 196, and it is equals to SY squared. SY is 2, therefore SY squared is 2 squared, that is 4, plus QY squared. So in total, we found out that 196 equals to 4 plus yq squared. We subtracted 4 from this equation, and we found out that 196 minus 4 is 192 equals to yq squared. We substituted 192 by 64 times 3, so 64 times 3 equals to yq squared. Here we took out of this equation, and we found out that yq, that means inside yq equals to the square root of 64, that is 8. Inside out we left only with 3. So in total yq equals to 8 times square root of 3 units in its length. This is the missing 9 segment yq, that is equals to 8 times square root of 3 units in its length. Quadrilateral ZCYQ is actually 1, 2, 3, 4 right angles, and therefore it is a rectangle. We know that the opposite sides of a rectangle are equal to each other. So in rectangle CZQY, side QY must be equal to the opposite side CZ. But QY is 8 times square root of 3, therefore the opposite side CZ must be also equal to 8 times square root of 3 units in its length. And here we actually have the small quadrilateral CFTS. Inside the small quadrilateral we have 1, 2 threaders, and therefore this warping segment must be equal to 90 degrees inside. Therefore quadrilateral CFTS is a rectangle, and we know that the opposite sides of the rectangle are equal to each other. So in rectangle CFTS, side ST must be equal to side CF. But ST is 8, therefore the opposite side CF must be also equal to 8 units in its length. So EF in total equals to 5 plus 4 times square root of 6, but plus 8 times square root of 3 plus 8. This is the length of the rectangle, and EH is the width of this rectangle, that is 16. So 16 times the length EF is the area of this rectangle EFQH. Because again, the area of rectangle EFQH equals to the width times the length. The width is the edge and the length is the F. Again, the width is the edge and the length is the F. So the width EH is 16, and EF in total equals to EA plus AZ plus ZC plus CF. So it is 16 times EA. EA is 5 plus AZ. AZ is 4 times square root of 6 plus ZC, that is 8 times square root of 3 plus CF, that is 8. So in total 16 times 5 plus 4 times square root of 6 plus 8 times square root of 3 plus 8 equals to the area of this big rectangle EFQH. The value of this expression is 586.47 square meters. So if you found out the area of this rectangle EFQH is equal to 586.47 square meters in its size. We finish with the first question. In the next step, I presented to you the second question, and we solved the second question by using two different methods. Our task in the first question is to find out the area of this circle. So we start with the first method. In the domain we have a circle. This is called AB, this is equal to 8 units in its length. This is called PQ, this is equal to 6 units in its length. This is again PMQ, this is equal to 90 units in size. Again, our task is to find out the area of this circle. So first of all, I presented to you rule 29 and implemented rule 29 in our drawing. If it's quickly rule 29, according to rule 29, peripheral angles that are set on the same arc are equal to each other. In the drawing we have a circle. This is peripheral angle BDC, this is subset on arc BC. This is peripheral angle BEC, this is subset on the same arc BC. and because of the fact that those two peripherical subset on the same arc BC, they must be equal to each other in their sizes. This is to say alpha equals to beta. So peripherical subset on the same arc are equal to each other in their sizes. According to this rule, rule 29. We can implement rule 29 in our drawing. One code in our drawing. This is peripherical BAQ that subtend on arc BQ. Likewise, this is peripherical QPB that subtend on the same arc BQ. And because of the fact that those two peripherical subtend on the same arc, they must be equal to each other in their sizes. So if the size of this peripherical BAQ equals to alpha, then the size of this peripherical PPQ must be also equal to alpha because they both subtend on the same arc BQ. In the next step, we will focus on this arc AP. This is peripherical ABP that subtend on arc AP. Likewise, this is peripherical angle PQA that subtend on the same arc AP. And because of the fact that those two peripherical subtend on the same arc, they must be equal to each other in their sizes. So if the size of this peripherical is beta, then the size of this peripherical must be also equal to beta. In the next step, we define the center of this area. This point is point O. I presented to you rule 13 and we implement rule 13 in our drawing. According to rule 13, the center angle is twice as large as the peripherical subtended on the same arc or the same chord. So in the drawing we have a circle. This is peripherical ACB that subtend on arc AB. This is center angle AOB that subtend on the same arc AB. And because of the fact the peripherical subtend on the same arc as the center angle must be twice as big as the peripherical. The peripherical ACB equals to theta, therefore the center angle AOB that subtend on the same arc AB must be equal to 2 theta. So according to this rule, rule 13, the center angle is twice as big as the peripherical that subtend on the same arc. We can implement rule 13 in our drawing. When put in our drawing, I do center angle POA that subtend on arc AP. But we have peripherical PQA that subtend on the same arc AP. Therefore, the center angle POA must be twice as big as this peripherical PQA that subtend on the same arc AP. The size of peripherical PQA is better, therefore the size of the center angle POA must be equal to 2 beta, according to rule 13. Likewise, if you focus on this arc BQ, we have peripherical BAQ subtend on arc BQ and it is equal to alpha. Therefore, center angle BOQ that subtend on the same arc BQ must be equal to 2 alpha, according to rule 13. In the next step, we define the angle POQ. This angle is X and this angle AOB is Y. And we have the rule that the sum of the angles around any point is equal to 360 degrees. So the sum of the angles around point O must be equal to 360 degrees. So which angles we have around point O, that is the center of the circle, we have 2 alpha plus 2 beta plus x plus y equals to 360 degrees. And again, if you focus on point O, the sum of the angles around point O must be equal to 360 degrees. That is to say, 2 alpha plus 2 beta plus x plus y, in total they must be equal to 360 degrees. But we already found out that 2 alpha plus 2 beta equals to 180 degrees. Again, 2 alpha plus 2 beta equals to 180 degrees. Therefore, we can substitute 2 alpha plus 2 beta by 180 degrees. So 180 degrees plus x plus y, in total they must be equal to 360 degrees. Here we subtract 180 degrees from this equation, and we finally found out that x plus y equals to 360 degrees minus 180 degrees is 180 degrees. So she found out that x plus y equals to 180 degrees. In the next step, I presented to you Rule 30, and we implemented Rule 30 in our drawing. According to Rule 30, center angles that subtend on equal chords are equal to each other. In the drawing we have a circle, we have center angle COD is equal to alpha degrees in size, and it subtends on chord CD. Likewise, we have center angle BOA that subtends on chord AB, and it is equal to beta degrees in size. So if chord AB is equal to chord CD, those two center angles must be equal to each other in their sizes. That is to say, alpha equals to beta. So if center angles subtend on equal chords, they must be equal to each other in their sizes. So if chord AB equals to chord CD, then those two center angles must be also equal to each other in their sizes. That is to say, alpha equals to beta. So we can implement Rule 30 in our drawing. So actually, copy this circle in a new page. Then I copied center angle AOB is equal to y degrees in size and subtend on chord AB in the new circle. The new circle is identical to this original circle. This is the new circle. I copied center angle AOB from the original drawing. Center angle AOB subtend on chord AB, and it is equal to 8 units in its length. Then from point B, I draw a chord that is equal to 6 units in its length. So BC equals to 6 units in its length according to our construction. Then we join points O and C together by straight line. By doing this construction, we get the center angle BOC. The center angle BOC subtend on chord BC that equals to 6 units in its length. And because of the fact the center angle, this center angle POQ also subtend on chord PQ that is also equals to 6 units in its length, according to Rule 30, center angles that subtend on equal chords must be equal to each other in their sizes. So those two center angles, they both subtend on chord that is equal to 6 units in its length, and therefore they must be equal to each other in their sizes. But the size of this center angle is x, therefore the size of this center angle COB must be also equal to x degrees in its size according to Rule 30. Okay, so in total we found out that the big angle AOC equals to x plus y, but we already found out that x plus y equals to 180 degrees. So the big angle AOC equals to 180 degrees. And we know that any angle that is equal to 180 degrees in its size, it is defined as a diameter. Any angle that is equal to 180 degrees in its size, it is defined as a straight line. So AC, angle AOC equals to 180 degrees in its size, therefore AC is a straight line. AC is a straight line, but AC is a straight line that touches the circle at 2 points, A and C. Therefore AC is a chord. AC is a chord that passes through point O, that is the center of the circle, and we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore AC that passes through the center of the circle, that is point O, must be the diameter of the circle. So AC is the diameter of the circle. Now we can implement Rule 7. According to Rule 7, if a peripheral angle subtend on the diameter of the circle, then it is equal to 90 degrees in its size. So in the one we have a circle. This is peripheral angle ACB that subtend on chord AB, that is the diameter of the circle, and therefore peripheral angle ACB must be equal to 90 degrees in its size. So according to Rule 7, any peripheral angle that is equal to 90 degrees any peripheral angle that subtend on the diameter must be equal to 90 degrees in its size. We can definitely implement Rule 7 in our drawing. Why? Because in our drawing we have peripheral angle ABC that subtend on AC, that is the diameter of the circle, and therefore according to rule 7, it must be equal to 90 degrees in size. So angle ABC equals to 90 degrees in size according to rule 7. In the next step, I copied the right triangle ABC in a new page and implemented to this right triangle ABC the particular theorem. AC is the diameter, that is 2R, AB is 8, and BC is 6. So okay, this is the right triangle ABC, that is the commit of the original domain. In this right triangle ABC, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. AC is 12, therefore AC squared is 12 squared. 12 squared is 4 squared. And it is equals to AB squared. AB is 8, therefore AB squared is 8 squared, that is 64, plus BC squared. BC is 6, therefore BC squared is 6 squared, that is 36. 64 plus 36 is 100, so 4R squared equals to 100. Here we divided this equation by 4, and finally found out that R squared equals to 100 over 4 is 25. So R squared equals to 25. Here we took out of this equation, and finally found out that R, the radius of this circle, is equal to the square root of 25 is 5. So the radius of this circle R equals to 5 units in its length. Our test is to find out the area of this circle. Actually, we know that the area of this circle equals to pi times the radius of the circle squared. Therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle is R, therefore the radius squared is R squared. So in total, the area of our circle must be equal to pi R squared. But R is 5, therefore R squared is 5 squared, that is 25. So in total, we found out that the area of this circle equals to either 25 pi square units in size. So in terms of numbers, the area of this circle equals to 78.54 square units in size. We finish with the first method. In the next step, I presented to you how to find out the area of this circle according to the second method. In the second method, we used some of the field that we already found out in the first method. In the first method, we have already found out that those two angles are both equal to alpha. Those two angles are right angles. So, in the right triangle A and B, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in the triangle. And likewise, in this right triangle PMQ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third angle must be equal to 90 degrees minus alpha, according to the rule that the sum of the angles in a triangle is equal to 180 degrees. It is very easy to see that those two triangles are similar to each other according to angle similarity rule. That is to say, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So if you found out that all the triangles of this right triangle A and B are corresponding equal to all those triangles of the right triangle P and Q, and therefore those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AB of the right triangle ABM over side PQ of the right triangle PMQ equals to side AM of the right triangle AB over side PM of the right triangle PMQ, and it is equals to side MB of the right triangle AB over side QM of the right triangle AMQ of the right triangle PMQ. We derive that AB over PQ equals to AM over PM equals to MB over QM. AB is 8, PQ is 6. We divided both the numerator and the denominator of this number by 2. 8 over 2 is 4, and 6 over 2 is 3. So 4 first equals to AM over PM. Here we multiply both the numerator and the denominator of this number by A, and we got that 4A over 3 equals to AM over PM. What is the meaning of this equation? It means that if AM equals to 4A, then PM must be equal to 3A. Likewise, so here, if AM equals to 4A, then PM must be equal to 3A. Likewise, those two sides of the equation also equal to each other. So here we have 4/3 equals to MB over QM. So 4/3 equals to MB over QM. If we multiply both the numerator and the denominator of this number by B, we found out that 4B over 3B equals to MB over MQ. What is the meaning of this equation? It means that if MB equals to 4B, then QM must be equal to 3B. So if MB equals to 4B, then MQ must be equal to 3B. We know that PB is a chord in this circle. PB is a chord, it is absolutely a straight line. So if you focus on the right side of the straight line PB at point M, here the sum of the angles must be equal to 180 degrees according to all three. All three said that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the right side of PB at point M? We have this angle that is a right angle plus this missing angle. In total must be equal to 180 degrees according to all three. Therefore this missing angle must be equal to 90 degrees in its size. In the next step I copied the right angle BMQ in a new page and implemented the Pythagorean on this right angle BMQ. So this is the right angle BMQ that I copied from the original drawing. This right angle BMQ, BQ square equals to BM square plus MQ square. BQ is the missing side, so we leave this it is. So it is BQ square equals to BM square. BM is 4B, therefore BM square is 4B square, that is 16B square plus MQ square. MQ is 3B, therefore MQ square is 3B square, that is 9B square. 16B square plus 9B square is 25B square. So BQ square equals to 25B square. We took all of the equation and found out that BQ equals to the square root of 25, that is 5, times square root of B square, that is B. So total BQ equals to 5B. This is 970BQ, that is equals to 5B. In the next step, we calculated the rectangle ABQ in two different methods and created an equation that said that the rectangle ABQ according to the first method must be equal to the rectangle ABQ according to the second method. According to the first method, we calculated the rectangle ABQ according, in the following way. The area of the triangle equals to the base of the triangle times the height of the base over 2. We choose the base as AQ and the height is MB over 2. So according to the first method, the area of the triangle ABQ equals to the base AQ times the height of the base BM over 2. According to the second method, the area of the triangle ABQ equals to AB times BQ times sinus angle ABQ over 2. Again, according to the second method, the area of the triangle AB equals to AB times BQ times sinus angle ABQ over 2. We have two both sides of the equation, so 2 will get cancelled. In order to find out the value of sinus angle ABQ, we implemented the law of sines in our drawing. The law of sines is so in any triangle. This is triangle ABC that could be any triangle. Side AB equals to C units in itself, side AC equals to B units in itself, and side BC equals to A units in itself. In this triangle ABC that could be any triangle, the following version is true that A over sinus alpha equals to B over sinus beta equals to C over sinus gamma. And it is equal also to 2R. 2R is the diameter of the circle that blocks this triangle. We can implement the law of sines in our drawing. Why? Because in our drawing we have triangle ABQ that is blocked by this circle. According to the law of sines, AQ over sinus angle ABQ equals to 2R. Again, AQ over sinus angle ABQ equals to 2R. Again, AQ over sinus angle ABQ equals to 2R. Here we multiply this equation by sinus ABQ and we divide it by 2R in order to find out the value of sinus ABQ, and found out actually that sinus ABQ equals to AQ over 2R. So we can substitute sinus angle ABQ by AQ over 2R. We did it and we found out that AQ times AB equals to AB times BQ, and sinus angle ABQ is AQ over 2R. Here we have AQ on both sides of the equation, so AQ will get cancelled. After we cancel AQ, we found out that BM equals to AB times BQ over 2R. Here we multiplied this equation by r, and we divided by bm by simultaneously, and found out actually that r, the radius of this circle, is equal to AB times BQ over 2 times MB. AB is 8, BQ is 5B, over 2 times BM. BM is 4B. We have 8 in the denominator, and 2 times 4 is 8 in the denominator. So those two expressions will get cancelled. B over B is 1, so B also will get cancelled. And we left only with 5. So the radius of this circle, r equals to 5. Our test is to find out the area of the circle. Actually, we know that the area of any circle equals to pi r squared. Pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. But the radius of our circle squared is r squared. So the area of our circle must be equal to pi r squared. But r is 5, therefore r squared is 5 squared, that is 25. So in total, we found out that the area of this circle, according to the both methods, it is equal to either 25 pi square units in size. So in terms of numbers, the area of this circle equals to 78.54 square units in its size. Okay, thank you very much.